Welcome to the deep dive. Today we're tackling a really big question, one that's, puzzled thinkers forever. What is time?
Right. Is it just ticking along, a dimension, something else?
Exactly. And one of you actually sent in this fascinating idea suggesting time isn't fundamental at all, that it emerges.
Yeah, we've been digging through those pasted text sources you sent, and they propose something, well, pretty revolutionary.
Forget the clock on the wall, basically.
Pretty much. These sources argue time comes from something much deeper.
Okay, let's try and unpack this. So the core idea, as I understand it, is that time emerges from how energy, information, and this other thing, coherence, interact within a system.
That's the gist of it. Yeah, it's not a river flowing through a landscape.
It's like the river is the interaction.
Precisely. The way the water, the land, everything interacts creates the flow. It's a totally different way of looking at, well, existence.
Okay. Sounds a bit heady, I admit.
It can be, yeah. But our mission here is to explore these core ideas from your sources, make them clear, and hopefully reveal some pretty surprising connections.
Those aha moments.
That's the goal, where things just click.
All right, so let's dive into what these sources are calling the Emergent Time Equation.
Yeah.
The central idea, time isn't fundamental, like space maybe. It just bubbles up.
It emerges, yeah. It's a property that arises from the interactions within a system. Not the stage, but like a consequence of the play itself.
Okay, and the first big shift in thinking here is that time isn't constant, not just ticking away.
Exactly, not just there in the background. It arises from this dynamic relationship between energy, information, and coherence.
Energy. We kind of get that. Makes things happen. But the sources link energy and time in a weird loop, right?
Yeah, it's interesting. Energy drives change, obviously. You know, battery powers a motor. Things happen over time.
So, standard stuff.
But the flip side in this model is that change defines energy. If nothing ever changed in a system, could you even say it has energy?
Never thought of it that way.
Energy is the capacity for change. So time and energy are like fundamentally linked. You can't really separate them in this view.
Okay, I think I'm following that recursive link.
Yeah.
But coherence, that feels a bit fuzzier. What exactly do the sources mean by coherence?
Right. Coherence, according to these texts, is about how much the parts of a system stay in a consistent, organized relationship over time. Think of it as how in sync everything is.
Orderliness.
Sort of, yeah. Order. It's got a mathematical value, C, between 0 and 1. 0 is total chaos, no sync at all.
Like gas molecules bouncing around.
Exactly. And 1 is perfect order, like a perfect crystal lattice or, a dancer's perfectly synchronized.
Okay, so more order, more coherence.
Leads to a more defined experience of time, according to this theory. Higher coherence, more time happens in a structured way.
Wow, okay. Order creates time in a sense.
What about the next piece?
Information density.
Yeah, information density. And importantly, it's not just about how much raw data you can cram in.
Not just gigabytes per cubic inch.
No, it's about meaningful, distinguishable connections within the system, the structure. Think of a library full of identical blank books versus one with fewer but diverse, interconnected novels.
The connections matter, the relationships between the stories.
Precisely. That second library has higher meaningful information density. And the sources suggest systems tend to evolve from low density, like simple rock, towards higher density, like a complex gas cloud or ecosystem.
But hang on, the sources also said something counterintuitive, that a small, highly connected system could be more information dense than something huge but static.
Yes, that's a key point. It's not about sheer size or mass. It's about the complexity of the interactions.
Like quantum entanglement, a few connected particles.
Exactly like that. Those few entangled particles, deeply linked, could hold more structured, non-redundant information than, say, a giant inert asteroid. The math they use relates it to something called Kolmogorov complexity per unit volume, essentially the shortest description of the system's structure.
Okay, so energy, coherence, information density. If you dial them all down to absolute zero, no energy, no order, no connections, what happens to time then?
According to this model, that's a timeless state. Existence itself, as we understand it, ceases. Not just empty space, but the complete absence of the conditions for time.
Right. No ingredients, no cake.
Something like that.
Okay, so we have the conceptual pieces. Energy driving change, coherence providing order, information density measuring connections. How does this all fit together in that emergent time equation they mentioned?
So the core relationship they propose is T, FC, IE. Time is some function of coherence, information, and energy. The main form they explore is T equals the square root of C times I over E.
Okay. TECC times Fra NUC. So time goes up with more order and more information.
But it goes down as energy E, the rate of change increases. More change happening faster means less emergent time experience within that system, relatively speaking.
Interesting inverse relationship with energy. So how are C, I, and E defined mathematically in this framework? Let's start with C, coherence.
Coherence, C, is defined as the sum of maintained geometric relationships between parts, divided by the maximum possible geometric order, ZIIG, GGI,
So G's like how well parts maintain their structural relationship.
Yeah, think symmetries, specific distances, phase alignments, how much of the potential order is actually realized and maintained.
Okay, a measure of geometric stability. Got it. What about I, information density?
Information density I is given as 1 di. A chi is that adjusted Kolmogorov complexity, basically the length of the shortest program to describe the system's meaningful structure.
Right, the non-redundant info.
Exactly. Divided by the volume, V. So more complex structure per unit space means higher I.
Makes sense. And E energy.
Energy E is defined as 1 EI dt Ti dt, but the rate of change of that information state with respect to some reference time frame.
There's that loop again. Energy is the speed of information change.
Precisely. Which directly ties back into how time itself emerges. It's all interconnected.
Okay, so we have a formula, definitions.
Okay.
But if this is going to be more than just a neat idea, it needs to make testable predictions, right? And maybe help with some big physics headaches.
Absolutely. And the sources do outline potential tests and some really, well, revolutionary implications. One of the biggest hopes is bridging quantum mechanics and general relativity.
Holy grail. How could this possibly help?
By proposing this deeper layer, the CIE interplay from which both quantum effects and space-time might emerge. Maybe the conflicts we see between QM and GR aren't fundamental, but arise because we're treating time as absolute, when it might behave differently based on the local C, I, and E values at different scales.
So time itself could be the missing link, behaving differently in the quantum world versus the cosmos.
That's the suggestion. It offers a potential common ground.
What about closer to home? Our own experience. Aging.
Yeah, the framework touches on that too. Subjective time, consciousness, maybe linked to neural coherence, the C value in our brain activity, and the energy dynamics, E higher coherence, might mean a richer sense of the now.
Fascinating. And aging. You mentioned QMT.
Right, quantum mitochondrial tracking. The idea here is that aging isn't just wear and tear, but maybe a gradual loss of coherence, C, and informational integrity within our cells, a decrease in that internal sync.
So getting older is fundamentally about losing internal order and information stability.
That's the hypothesis stemming from this model, yeah. It reframes aging.
And the universe. Big Bang, heat death.
It offers new angles there, too. How did time start with the Big Bang? Maybe as C, I, and E first emerged, how might it end? Perhaps as these factors change drastically, it even connects to things like the holographic principle, the idea that information about a volume can be encoded on its surface. High I, potentially enabled by intricate connections.
Mind. Blown. Okay, let's ground this a bit. How can we actually test this? Give me a couple of concrete, testable predictions from the sources.
Okay, one really interesting one is called quantum coherence time dilation.
Sounds fancy. What's the core idea?
The prediction is, if you have two quantum systems with the same energy, but different levels of internal coherence, C, the one with higher coherence should maintain its delicate quantum state, like superposition, for longer than standard theory predicts.
So more order makes quantum states last longer.
Essentially, yes. Higher C leads to a slower decay relative to its internal dynamics, extending its quantum lifetime.
And how would you test that? In a lab.
You'd prepare identical quantum systems, but manipulate them to have different measurable coherence levels, C1 and C2, keeping their energy E the same. Then you measure how long they stay in superposition.
And the prediction is?
The prediction from the equation is specific. The ratio of their decay times should equal the square root of the ratio of their coherence values. Decay time ratio phi's EC1C2. That's different from what current models would say.
Wow, okay, that's very specific. What's another testable idea?
Another one is biological temporal coherence. This suggests that how fast organisms or cells age isn't just about metabolism, energy use.
There's more to it.
Yeah, it also depends on their internal coherence, C, and information density, I. Higher C, and I should mean slower aging, even if the energy expenditure is the same.
So more organized, complex cells might age slower. How do you test that?
You could take identical stem cell lines, find ways to experimentally boost or reduce coherence, C, in one line compared to another, keeping their metabolic rate, E, similar.
Tricky, but maybe possible.
Potentially. Then you track standard aging markers, telomeres, epigenetic clocks, things like that. The prediction, assuming equal energy, E1, E2, is that the ratio of their aging rates would follow aging rate ratio 461 times I1 C2 times I21.
Again, a very specific prediction based on measurable quantities. These could really put the theory through its paces. Now, you mentioned coherence as a geometric constraint. Can you expand on that? What does that mean practically?
Sure. Thinking of coherence, C geometrically makes it less abstract. It's about quantifying things like structural symmetries in a molecule, or the number of holes in a network topology, things that don't change easily.
Like the shape, the structure.
Exactly. And how stable those geometric features are over time. Correlation links between parts, phase relationships and oscillations, like dancers maintaining formation. That's high geometric coherence.
So it's not just order in a vague sense, but measurable physical structure and its persistence.
Right. And this links up nicely with stuff we already know in physics. Wave coherence is about phase relationships geometry. Phase transitions, like water to ice, involve changes in geometric symmetry. Order parameters in materials science, geometric phases in quantum mechanics, they all fit this picture.
So it connects to existing concepts.
It does. And the beauty is this geometric view of coherence might apply at all scales: quantum, molecular, biological, even neural networks.
That multi-scale idea is powerful. Okay, let's loop back to those physics paradoxes. How could emergent time help with something like why photons don't experience time?
Well, looking at the equation, TAT times FarcIE times frac. For a photon, a light wave, coherence, C, is extremely high, perfectly synchronized waves.
Maximum order.
Kind of, yeah. The idea or speculation is that this extremely high C, balanced perhaps with its I and E, might drive the emergent time in the photon's own reference frame towards zero. The perfect order essentially stops its internal clock.
Fascinating. The order negates time. What about the black hole information paradox? Does information really get destroyed?
This framework offers another possibility. Maybe a black hole is maximum information density because everything's crushed together.
But minimum coherency because of the chaos near the singularity.
Exactly. So maybe information isn't destroyed, but transformed into a state defined by this extreme high I, low C condition. A state where emergent time behaves so differently, the information is just encoded in a way we don't understand yet.
So not gone, just changed state.
Potentially. And the singularity itself. Maybe infinite energy density E, but near zero coherence, C, leads to, well, who knows what kind of time. It suggests these paradoxes arise from assuming time is constant, not emergent and variable.
What about the event horizon? The different experiences inside and out?
That could be down to the dramatic shift in C, I, and E across that boundary. Different conditions, radically different emergent time.
It offers a whole new language to talk about these problems. You also mentioned a reflective method. What's that about?
It just highlights how interconnected C, I, E, and T are in this model. Remember, E equals di dt. Energy is the rate of change of information over time.
Right.
So energy affects time, but time is part of the definition of energy via change. And coherence affects information stability, energy flow affects coherence. It's all looped together.
It's a feedback system, like the observer effect in quantum mechanics. Measuring something changes it.
That's a great analogy, yeah. The act of change, driven by energy, defines the time in which other changes related to information and coherence occur. It's intrinsically self-referential.
This is, yeah, a really profound shift. How does it stack up, potential-wise? Is this an EMUM-C moment?
The sources definitely suggest that potential. Like EMM-Sci, it tries to unify things, offers a new foundation. It could bridge QM and GR, explain consciousness, aging, cosmology.
Planet.
But EM-Sci is simple, elegant, and massively experimentally verified. This emergent time idea is much more complex and, frankly, still very theoretical.
So what's needed to push it forward, to see if it holds water?
Rigorous mathematical development, first off, then deriving more specific, unique, quantitative predictions, things that only this theory predicts, and then, crucially, designing and doing the experiments like those coherence tests we discussed.
Testing, testing, testing.
Exactly. And seeing if it can explain phenomena that current physics can't. That would be huge.
Well, this has been an absolutely fascinating deep dive. It really makes you question the nature of time itself. Maybe it's not the background constant we always assumed.
That really is the core takeaway, isn't it? Your sources offer this radical new perspective. time emerging from energy information coherence. And hopefully, looking at things like light or black holes through this lens gave you some of those aha moments we talked about.
It's complex for sure and clearly an evolving idea, but the potential, unifying science, challenging basic assumptions. It's exciting stuff.
It is.
So here's a final thought for you, the listener, to mull over. If time, something so seemingly fundamental, could actually be an emergent property, what else that we take for granted might also arise from deeper interactions? What other bedrock assumptions about reality are maybe not so solid?
Makes you think, doesn't it?
It certainly does. Thank you for joining us on this deep dive, and a huge thank you to our listener for sending in these incredibly thought-provoking sources.